ISO 10303 is an ISO standard for the computer-interpretable representation and exchange of product in manufacturing information. Its official title is Automation Systems and Integration, Product Data Representation and Exchange. It is known informally as STEP, which stands for Standard for the Exchange of Product Model Data. ISO 10303 can represent 3D objects in computer-aided design and related information. Overview. The international standard's objective is to provide a mechanism that is capable of describing product data throughout the life cycle of a product, independent from any particular system. The nature of this description makes it suitable not only for neutral file exchange, but also as a basis for implementing and sharing product databases and archiving. Typically, STEP can be used to exchange data between CAD, computer-aided manufacturing, computer-aided engineering, product data management, enterprise data modeling, and other CACS systems. STEP addresses product data from mechanical and electrical design, geometric dimensioning and tolerancing analysis and manufacturing, as well as additional information specific to various industries such as automotive, aerospace, building construction, ship, oil and gas, process plants and others. STEP is developed and maintained by the ISO Technical Committee TC 184, Automation Systems and Integration, Subcommittee SC4, Industrial Data. Like other ISO and IEC standards, STEP is copyright by ISO and is not freely available. However, the 10303 Express scheme is freely available, as of the recommended practices for implementers. Other standards developed and maintained by ISO TC 184, SC4I, ISO 13584 PLIB, Parts Library, ISO 15531 Mandate, Industrial Manufacturing Management Data, ISO 15926 Process Plants including oil and gas facilities life cycle data, ISO 18629 PSL Process Specification Language, ISO 18876 IIDEAS Integration of Industrial Data for Exchange, Access, and Sharing, ISO 22745 Open Technical Dictionaries and their application to master data, ISO 8000 Data Quality. STEP is closely related with PLIB. History. The evolution of STEP can be divided into 4 release phases. The development of STEP started in 1984 as a successor of IGES, SET and VDAFS. The initial plan was that STEP shall be based on one single, complete, implementation-independent product information model, which shall be the master record of the integrated topical and application information models. But because of the complexity, the standard had to be broken up into smaller parts that can be developed, balloted and approved separately. In 1994-95 ISO published the initial release of STEP as international standards with the parts 1, 11, 21, 31, 41, 42, 43, 44, 46, 101, AP 201 and AP 203. Today AP 203 configuration-controlled 3D design is still one of the most important parts of STEP and supported by many CAD systems for import and export. In the second phase, the capabilities of STEP were widely extended, primarily for the design of products in the aerospace, automotive, electrical, electronic, and other industries. This phase ended in the year 2002 with the second major release, including the STEP parts AP 202, AP 209, AP 210, AP 212, AP 214, AP 224, AP 225, AP 227, AP 232. Basic harmonization between the APs, especially in the geometric areas, was achieved by introducing the application-interpreted constructs. A major problem with the monolithic APs of the first and second releases is that they are too big, have too much overlap with each other, and are not sufficiently harmonized. These deficits lead to the development of the step modular architecture. This activity was primarily driven by new APs covering additional life cycle phases such as early requirement analysis and maintenance and repair, and also new industrial areas. New editions of the previous monolithic APs on a modular basis have been developed. The publication of these new editions coincided with the release in 2010 of the new ISO product SMRL, the Step Module and Resource Library, that contains all step resource parts and application modules on a single CD. The SMRL will be revised frequently and is available at a much lower cost than purchasing all the parts separately. In December 2014, ISO published the first edition of a new major application protocol, AP 242, managed model-based 3D engineering, that combined and replaced the following previous APs in an upward compatible way. AP 201, explicit drafting, simple 2D drawing geometry related to a product. No association, no assembly hierarchy. AP 202, associative drafting, 2D, 3D drawing with association, but no product structure. AP 203, configuration-controlled 3D designs of mechanical parts and assemblies. AP 204, mechanical design using boundary representation. AP 214, core data for automotive mechanical design processes. In addition, AP 242 Edition 1 contains extensions and significant updates for geometric dimensioning and tolerancing, kinematics, tessellation. Two APs had been modified to be directly based on AP 242 and thus become supersets of it. AP 209, composite and metallic structural analysis and related design. AP 210, electronic assembly, interconnect and packaging design, the most complex and sophisticated step. The development of a second edition of AP 242 has started, which is extending the scope for electrical harness. Structure. Step is divided into many parts, grouped into environment parts 1x, description methods, express X parts 2x, implementation methods, step file, step XML, SDI parts 3x, conformance testing methodology and framework, integrated data models. The integrated resources, consisting of parts 4x and 5x, integrated generic resources parts 1xx, integrated application resources PLIB ISO 13584-20 parts library, logical model of expressions parts 5xx, application interpreted constructs parts 1xxx, application modules. Top parts parts 2xx, application protocols parts 3xx, abstract test suites for APs parts 4xx, implementation modules for APs. In total, step consists of several hundred parts, and every year new parts are added and new revisions of older parts are released. This makes step the biggest standard within ISO. Each part has its own scope and introduction. The APs of the top parts, they cover a particular application and industry domain and hence are most relevant for users of STEP. Every app defines one or several conformance classes suitable for a particular kind of product data exchange scenario. STEP is primarily defining data models using the Express modeling language. Application data according to a given data model can be exchanged either by a STEP file, STEP XML, or via shared database access using SDAI. Every app defines a top data models to be used for data exchange, called the application interpreted model, or in the case of a modular app called module interpreted models. These interpreted models are constructed by choosing generic objects defined in low-level data models and adding specializations needed for the particular application domain of the app. The common generic data models are the basis for interoperability between APIs for different kinds of industries and life cycle stages. In APIs with several conformance classes, the top data model is divided into subsets, one for each conformance class. The requirements of a conformance step application are implementation of either a preprocessor or a post-processor, or both, using one of the step implementation methods, step file, step XML, or SDAI for the AIM data model, and supporting one or several conformance classes of an app. Originally, every APIs was required to have a companion abstract test suite, providing test purposes, verdict criteria, and abstract test cases together with example step files. But because the development of an ATS was very expensive and inefficient, this requirement was dropped and replaced by the requirements to have an informal validation report and recommended practices how to use it. Today, the recommended practices are a primary source for those going to implement STEP. The application reference models is the mediator between the ARM and the AIM. Originally, its purpose was only to document high-level application objects and the basic relations between them. IDEF1X diagrams documented the app of early APIs in an informal way. The ARM objects, their attributes and relations are mapped to the AIM so that it is possible to implement an app. As APIs got more and more complex, formal methods were needed to document the ARM, and so Express, which was originally only developed for the AIM, was also used for the ARM. Over time, these ARM models got very detailed to the point that some implementations preferred to use the ARM instead of the formally required AIM. Today, a few APIs have ARM-based exchange formats standardized outside of ISO TC 184 SC4 PLM services within the OMG4 App 214 ISO 14649 data model for computerized numerical controllers for App 238. PLCSDEX is within Oasis 4 App 239. There is a bigger overlap between APIs because they often need to refer to the same kind of products, product structures, geometry and more. And because APIs are developed by different groups of people, it was always an issue to ensure interoperability between APIs on a higher level. The application interpreted constructs solved this problem for common specializations of generic concepts, primarily in the geometric area. To address the problem of harmonizing the ARM models and the mapping to the AIM, the STEP modules were introduced. They contain a piece of the ARM, the mapping, and a piece of the AIM, called MIM. Modules are built on each other, resulting in an indirected graph with the app and conformance class modules at the very top. The modular APIs are App 209, Composite and Metallic Structural Analysis and Related Design. App 210, Electronic Assembly, Interconnect and Packaging Design. App 221, Functional Data and Schematic Representation of Process Plants. App 236, Furniture Product Data and Project Data. App 239, Product Life Cycle Support. App 242, Managed Model-Based 3D Engineering. The modular editions of App 209 and 210 are explicit extensions of App 242. Coverage of STEP application protocols. The STEP APs can be roughly grouped into the three main areas: design, manufacturing and life cycle support. Design APs: mechanical AP 207, sheet metal die planning and design AP 209, composite and metallic structural analysis and related design AP 235, materials information for the design and verification of products AP 236, furniture product data and project data AP 242, managed model-based 3D engineering. Connectivity-oriented electronic and piping, ventilation, AP 210, electronic assembly, interconnect and packaging design. The most complex and sophisticated STEP AP 212, electrotechnical design and installation. AP 227, plant spatial configuration. Ship AP 215, ship arrangement AP 216, ship molded forms AP 218, ship structures. Others AP 225, building elements using explicit shape representation AP 232, technical data packaging, core information and exchange AP 233, systems engineering data representation AP 237, fluid dynamics has been cancelled and the functionality included in AP 209, manufacturing APs AP 219, dimensional inspection information exchange AP 223, exchange of design and manufacturing product information for cast parts AP 224, mechanical product definition for process plans using machining features AP 238, application interpreted model for computer numeric controllers AP 240, process plans for machined products. Life cycle support APs AP 239, product life cycle support AP 221, functional data and schematic representation of process plants AP 241, generic model for life cycle support of AEC facilities. The AP 221 model is very similar to the ISO 15926-2 model, whereas AP 221 follows the STEP architecture and ISO 15926-2 has a different architecture. They both use ISO 15926-4 as a common reference data library, a dictionary of standard instances. The further development of both standards resulted in English's general product modeling language that is application domain independent and that is proposed as a work item for a new standard. The original intent of STEP was to publish one integrated data model for all life cycle aspects, but due to the complexity, different groups of developers and different speed in the development processes, the splitting into several APs was needed. But this splitting made it difficult to ensure that APs are interoperable in overlapping areas. Main areas of harmonization are AP 212, 221, 227 and 242 for technical drawings with extension in AP 212 and 221 for schematic functionality, AP 224, 238 and 242 for machining features and for geometric dimensioning and tolerancing. For complex areas it is clear that more than one APs are needed to cover all major aspects. AP 212 and 242 for electromechanical products such as a car or a transformer. This will be addressed by the second edition of AP 242 that is currently under development. AP 242, 209 and 210 for electronic mechanical products. AP 212, 215, 216, 218, 227 for ships, AP 203, 214, 224, 240 and 238 for the complete design and manufacturing process of piece parts.